Bismillah ar-Rahman ar-Rahim. This video is about the differentiability of the characteristic function of a random variable x. Consider a random variable x that has a finite kth moment. This means that the expectation of x to the k and the expectation of magnitude x to the power k, these are finite numbers. If this is true, then we can differentiate the characteristic function, which is this expectation e to the I ux. The characteristic function can be differentiated k times, and the kth derivative is this expectation. This expectation looks as if we differentiate here what is inside the expectation with respect to u. So we get ix raised to the power k and then e to the iux. If we evaluate this kth derivative at u equals 0, this becomes 1, and we get I to the k expectation of x to the k. The kth derivative is also a uniformly continuous function. Let's start by showing that this expectation is finite. If the random variable x has a finite kth moment, apply the triangle inequality, the magnitude of the expectation is less than or equal to the expectation of the magnitude. The magnitude of I is 1. This exponential is in the form e to the power I times the real number, so the magnitude is also equal to 1. And we are left with the magnitude of x to the power k. So the magnitude of this expectation is less than or equal to the kth absolute moment of random variable x, which is assumed to be a finite number. So this is finite. We will make use of the following inequality. If we have a real number z, then the magnitude of the difference between e to the minus z and 1 plus iz, the magnitude of this difference is upper bounded by the minimum of two terms. 2 times the magnitude of z, that's one term, and another term is half z squared. Now back to our main theorem. We want to show that if the kth moment is finite, we can differentiate the characteristic function k times. So we do a proof by induction. Our initial focus will be the case in which k is equal to 1. So the statement is that if the random variable x has a finite first moment, then we can differentiate the characteristic function once. The plan is to study the magnitude of this difference. Here we have the candidate first derivative, and then we have here the characteristic function phi of u plus epsilon minus phi of u divided by epsilon. Note that this is the quantity that we study to investigate whether a certain function has a first derivative or not. The first step is to write down the characteristic functions using expectation, so that we can combine all the terms under one expectation, exploiting the fact that expectation is linear. So what we have here inside the magnitude is the expectation, and then we have 1 over epsilon, which is this. The characteristic function of u plus epsilon is expectation e to the I u plus epsilon times x. The characteristic function is expectation e to the I ux, and then we have this term here. Since we have 1 over epsilon as a common factor, we multiply here by epsilon. Here is everything written in terms of just one expectation. Then we apply the triangle inequality. Note that there is e to the iux that is common. So this is expectation of e to the iux, 1 over epsilon, and then we have e to the I epsilon x minus 1 minus I epsilon x. When we apply the triangle inequality, the magnitude of the expectation is less than or equal to the expectation of the magnitude. And when we take the magnitude inside the expectation, well, this has a magnitude of 1. So what we get is 1 over the magnitude of epsilon, and then we have the magnitude of this bracket here. Now we can make use of our inequality. Replace z by epsilon times x. And now this magnitude is upper bounded by the minimum of 2 times the magnitude of epsilon times the magnitude of x, and then the other term is 1/2 the magnitude of epsilon squared times the magnitude of x squared. Note that both terms have the magnitude of epsilon, so this minimum is equal to the magnitude of epsilon times the minimum of 2 times the magnitude of x, and then the second term is 1/2 the magnitude of epsilon, the magnitude of x squared. And this magnitude of epsilon is cancelled with this magnitude of epsilon in the denominator. So now our upper bound is the expectation of the minimum of these two terms. Can we take the limit inside? Can we interchange the order of limit and expectation? This quantity here is a minimum, and so the magnitude of whatever is inside the expectation is upper bounded by either one of these two terms. So let's upper bound this minimum by 2 times the magnitude of x. What is the expectation of the upper bound? The expectation of the upper bound is a finite number because it is assumed that x has a finite first moment. So what we have inside the expectation in magnitude can be upper bounded by a quantity 2 times the magnitude of x, and the expectation of the upper bound is a finite number. So by the dominated convergence theorem, we are allowed to interchange limit and expectation. We can take the limit inside. This limit of the expectation is the expectation of the limit. Now we need to take the limit of this quantity here. What is the limit of the minimum? This is the minimum of two non-negative quantities. So we have 0 as the lower bound, then we have this minimum. And again, we can upper bound a minimum by any of the two terms. When we tried to see whether we can apply the dominated convergence theorem, we upper bounded by this term here to exploit the fact that it is given that the random variable has a finite first moment. Now we will upper bound this minimum by this other term, which contains the magnitude of epsilon. This minimum is upper bounded by the second term here, 1/2 times the magnitude of epsilon times x squared. Now the upper bound, if we take the limit as epsilon goes to 0, will be 0. And so by the sandwich theorem, this limit is 0. And so whatever we have inside the expectation here is 0. Note that this expectation is an upper bound on this original quantity, which is also lower bounded by 0. So by applying the sandwich theorem again, this limit is indeed equal to 0. We have shown that the magnitude of this difference approaches 0 as epsilon tends to 0. So what we have inside the magnitude here tends to 0, and this limit is given by this expectation. And at the very beginning, we verified that in magnitude, this expectation is finite. Indeed, the characteristic function is differentiable, and this is its first derivative. Suppose that for a positive integer v, we assume that the characteristic function is differentiable v times, and its vth derivative is given by this expectation. We want to show that given this, then the derivative of order v plus 1 exists and is equal to this expectation here, provided that the random variable x has a finite moment of order v plus 1. The steps here are very similar to what we have just done. We will take this quantity. So this is the vth derivative of the characteristic function. We take the vth derivative evaluated at u plus epsilon minus the vth derivative evaluated at u, and then we divide by epsilon. We subtract this expectation. This is the candidate derivative of order v plus 1. So we subtract and we take the magnitude. We investigate the limit. We start by writing the derivatives of the characteristic function using the expectations. And when we do this, we get the expectation of 1 over epsilon and then this bracket here. We have e to the iux is a common factor. We apply the triangle inequality. By the triangle inequality, the magnitude of the expectation is less than or equal to the expectation of the magnitude. When we take the magnitude inside, e to the iux will disappear. And then we get the magnitude of x to the power v, and the remaining terms will appear here in this magnitude, e to the I epsilon x minus 1 minus I x times epsilon. And this magnitude here is exactly what we have encountered before. This is upper bounded by the minimum of, so this is upper bounded by the minimum of 2, the magnitude of epsilon, the magnitude of x, comma, and then we have 1/2, and then we have epsilon x squared. And we can take the magnitude of epsilon outside, and here we have the minimum of 2 times the magnitude of x, and then the second term will be 1/2 magnitude of epsilon and then x squared, as we can see here. Can we take the limit inside? Now, this quantity in magnitude is upper bounded by the magnitude of x to the power v, and then from the minimum, we can just upper bound using this term here. We have that the magnitude of this quantity, we don't really need to use magnitude because what we have inside the expectation is real valued and non-negative, but let's just keep it. This is upper bounded by the magnitude of x to the power v, and then from these two terms, we will use this one here, which is 2 times the magnitude of x. Note that in order to apply the dominated convergence theorem, we need to take whatever is inside the expectation and upper bound it in magnitude with something that does not depend on the variable with respect to which we are taking the limit. So here we need actually to upper bound using this term so that we get an upper bound that does not have epsilon in it. Now this upper bound is 2 times the magnitude of x to the power v plus 1. If we apply expectation to this upper bound, will we get a finite number? Yes, we get a finite number, assuming that random variable x has a finite moment of order v plus 1. Therefore, we can apply the dominated convergence theorem. We can take the limit inside. And now we want to take the limit. This is the term that has epsilon. And like we did before, this is the limit of the minimum. Well, this minimum is greater than or equal to 0, and it is less than or equal to one of the two terms. This time, we will take this as our upper bound, and this goes to 0 as epsilon goes to 0. By the sandwich theorem, the limit here inside the expectation is 0, so the expectation is equal to 0. This expectation is an upper bound on this magnitude here, and this magnitude is non-negative. So by the sandwich theorem again, it must be the case that this limit here is exactly equal to 0. And so the limit of this quantity as epsilon tends to 0, this is the derivative of order v plus 1. and it exists, and it is equal to this expectation here. We have shown that if the first moment is finite, then the first derivative exists. Now we have shown that if the derivative of order v exists, then the derivative of order v plus 1 exists. Combining these together, then we have our statement proved. If the random variable x has a finite kth moment, then the characteristic function can be differentiated k times. The last thing is to show that the kth derivative is uniformly continuous. Take the kth derivative evaluated at u1, evaluated at u2, compute the difference, take the magnitude. We want to show that this magnitude can be made arbitrarily small by choosing sufficiently close u1 and u2. Express the kth derivatives using the expectation. We will get this bracket. From this bracket, take e to the I u1 plus u2 over 2x as a common factor. We are left here inside the bracket with something that looks like e to the I theta minus e to the minus I theta, where theta is u1 minus u2 over 2 all times x. Using Euler, this is 2i sine theta. So in our case, this bracket is 2 times I times sine of u1 minus u2 over 2 times x. Apply the triangle inequality. We can take the magnitude inside. The magnitude of I is 1. The magnitude of this exponential is 1. We have this expectation now times 2, which is this 2 here. Let u1 minus u2 be eta. This is an upper bound on this magnitude as a function of eta, which is the difference between u1 and u2. We want to show that the limit of this expectation as eta tends to 0 is 0. This means that by choosing sufficiently close u1 and u2, this upper bound is sufficiently small, and so this magnitude can be made as small as we wish. So what is the limit of this expectation as eta tends to 0? Can we take the limit inside by applying the dominated convergence theorem? And the answer is yes. Whatever we have inside the expectation, it is upper bounded by this quantity, the magnitude of x to the power k, because the magnitude of the sign is upper bounded by 1. So we have an upper bound that does not depend on eta, which is the variable with respect to which we are taking the limit. And what is the expectation of the magnitude of x to the power k? That's assumed to be a finite quantity. So by the dominated convergence theorem, we are justified in swapping limit and expectation. We can take the limit inside, and because here we have sign of something times eta, then the limit is 0. We have expectation of 0, which is 0. By choosing u1 and u2 sufficiently close to one another, we can make this upper bound as small as we wish. This means that the kth derivative is indeed a uniformly continuous function.